Hey everyone, my name is Ketan. I'm a combined plan student currently pursuing my BS in computer science. I am a science research fellow.
And my name is Andrew Magid. I'm a current junior at Columbia College studying math and computer science, and I'm a John Jay Scholar.
This summer, Andrew and I worked at the Applied Math department as part of the C-Sure program, along with Oliver Lee, another student. Our project explored the dynamics of mining agents on cryptocurrencies.
So before we jump into our research, I want to give some background information about what a blockchain is, which is used by a lot of cryptocurrencies. A blockchain is just a decentralized and distributed list of records. And for example, for cryptocurrencies, this would store the transaction data. Now, these transactions data are stored in units called blocks, and these blocks are cryptographically linked in a chain. Now, if someone wanted to add a block to this chain, this is a process called mining. So somebody would solve a computational puzzle and verify these transactions and put this at the end of the chain. And for the purposes of our presentation, we're going to refer to one miner as one agent. And an important thing is that these agents or miners, once they publish a block, actually receive some reward for doing so.
So once a miner finds a block, they ought to immediately publish it, and that's called honest mining. But there are certain methods of mining where miners can withhold blocks once they find them and release multiple blocks at later periods of time. And research shows that these methods, which deviate from the honest protocol, which is encouraged by the blockchain protocol, actually give these miners more rewards. And with the emergence of mining pools, this attack, basically capitalizing on more rewards, is extremely dangerous. Any blockchain system with a peer-to-peer consensus protocol is vulnerable to this family of attacks.
And so from this, our next question was, how do these different mining strategies compare to one another under one set of assumptions, which allows us to actually fairly compare them? And also, is there a better way to model these behaviors and this process in general?
We identified four broad ways of block withholding attacks, which were deemed malicious. But what we realized was every study that individually looked at these methods used different sets of assumptions. It was extremely hard to compare the relative effectiveness to each other. And so that's where we came in. We parameterized using our own framework each of these agents using four parameters. Furthermore, we also generalized the description for blockchain in three parameters, and thus combining that, we created a modular and scalable simulation framework for agent blockchain interactions. Using this framework, we performed profitability and cost analyses on these strategies in a relative fashion.
So these were the findings of our research project, was to create this framework, which is extremely generalizable. We were able to abstract away these strategies or these agents from the simulation itself. So we were able to implement any strategy and compare them to one another, and also have any number of agents, which is a much more realistic modeling of the actual process. Additionally, we were also able to account for a type of interaction called effector flow within this model. And this makes our model much more realistic and much more accurate. And these two things, this abstraction as well as this accounting for defector flow, is something that hasn't been done before in other papers. We can see that our model is actually correct because we were able to replicate existing experiments and get extremely similar results to those other papers. So for example, this graph here shows a very similar trend that was observed by another simulator in another paper. It also allows us to see whether a strategy has a significant advantage over their counterparts. And also it shows us whether a cryptocurrency protocol is susceptible to these types of attacks or behaviors.
Making our simulation system scalable and modular came with a great advantage that was that we could develop a practical application to test existing Bitcoin-like blockchain protocols and see if deviant mining was taking place in real time. Specifically, given public data from a protocol, we could infer if some sort of deviant mining behavior was taking place. Our statistical method essentially looks at the profile of the existing protocol, looking at the kinds of mining pools that are involved, and look at the block creation times coming from real data, then compare that with synthetically generated data using our sets of simulations and looking at similarities. A high similarity would indicate that deviant mining was indeed taking place using one of the suites of strategies that we have currently studied so far. Although getting numerical results on this part is still future work, we think that this methodology is extremely promising.
So in summary, we were able to generalize this process to account for a much more accurate model of these malicious mining behaviors and be able to compare their effectiveness. And additionally, we were able to extend our model to include interactions like defector flow, which haven't been done by other models before. Thank you so much for listening. And if there are any questions, feel free to reach out to us at our emails.